All right, so we want to go over, first of all, to start with in this class, a review of the laws of probability. I'm not going to focus on proving them. I want to focus on remembering what they are and thinking about them intuitively. Okay, so there's going to be less of a focus on proof in this applied stats course, more of a focus on intuition and application. But we did start, we should remind you, of the axioms of probability. That's what you start with. I'm not going to fully set this up in terms of describing what sample spaces are and probability set functions. I'm going to assume from the reading that you've thought about those a little bit or remember them. I'm just going to go ahead and start and write out the axioms. One axiom is that the probability of any event is greater than or equal to 0. Actually, I don't remember if I'm listing these in the same order as the book. I probably do such a thing. Okay, they start off by assuming the probability of the entire sample space is 1. So S is the sample space. If you think in terms of outcomes, that's the set of all possible things that can happen. Sample spaces can be finite, they can be infinite. Might be good as we go along here to imagine a fairly simple example of flipping a fair coin 3 times. So that'll be sort of our example that we think about as we work through the axioms and properties of probability. Flip a fair coin 3 times. What's the sample space in that case? Well, you could get all 3 heads. You could get 2 heads and a tail. But you want to keep track of the different ways that can happen. You could get HHT, you could get HTH, or you could get THH. You could get 1 head and 2 tails, but that can happen in 3 different ways: HTT, THT, or TTH. And finally, you could get all tails. So that's, again, our simple example to think about as we go. That's the sample space. That's the collection of all possible outcomes, things that can happen. Now, could something not in this list happen? Well, theoretically, you could flip the coin and your dog could come running through the room and jump and eat the coin. But we don't think about that kind of thing because it's so rare that you don't worry about it, right? Keep things simple. The probability, essentially this is saying the probability of something happening is 1. Something in the sample space is going to happen. 100% chance. Second axiom is the non-negativity. The probability of any event A is never negative. It's always greater than or equal to 0. Could it ever equal 0? Yeah, some events have a probability of 0. If it was a fair coin, that's not going to happen. But if there was an unfair coin that never came up tails somehow, then the event that you get at least 1 tail would have 0 probability. And the only thing that has a positive probability would be all heads. Probability 1, if somehow you could magically make a coin that did that. But you don't want negative probabilities. You want them greater than or equal to 0. Third one is really an axiom, but it's got a name. It's called the addition rule for mutually exclusive events. Events, again, are subsets of the sample space. Mutually exclusive means there's no overlap. Okay, actually, they're pairwise mutually exclusive. If you take any 2 of them, there's not going to be any overlap. It's not just that the intersection of all of them is empty. It's that you take any 2 of them, there's not going to be any overlap. The probability of the union of them, where that union theoretically could go on forever. You could have infinitely many events here, is the sum of the individual probabilities. Usually we use this in the case where you've got two events, or maybe three, but in theory, you're saying it applies to any number of events, including a countably infinite number of events. So those are the axioms. And when you are doing probability theory, you assume these things are true. You don't prove them. It's the setup for everything else. You want to keep your axioms minimal and try to prove whatever you can from the axioms. Properties that can be proved from the axioms include, well, the probability of the empty set is 0. In other words, nothing is not going to happen. Something will happen. That's sort of the other side of the coin of axiom 1. Nothing is not going to happen. That's the empty set, the set with nothing in it. Something in the sample space has to happen. You can prove that based on these. Another property related to that, and maybe you'd want to prove this property before you prove property 4, is that the probability of A happening plus the probability of its complement happening, AC, the complement of A, equals 1, which of course is equivalent to saying the probability of the complement of A is 1 minus the probability of A, which is also equivalent to saying the probability of A is 1 minus the probability of the complement of A. In the context of our simple example, examples of mutually exclusive events could be the event A1 is you get 3 heads, A2 is you get exactly 2 heads, A3 is you get exactly 1 head, and A4 you get exactly 0 heads. Those would be examples of mutually exclusive events where the special addition rule works. Examples of not mutually exclusive events could include you get at least 1 head and you get no more than 2 tails. Those are really the same event, aren't they? You get at least 1 head and you get at least 2 heads. Think of those as 2 separate events. Those are not mutually exclusive. They can both happen at the same time. If you get 2 or more heads, then you got at least 1 head and you also got at least 2 heads. Example of a complement here. If A is the event that you get at least 1 head, then its complement is the event that you got 0 heads, right? As a set, but you can describe events with words. A is the event of getting at least 1 head. You can describe it in words like that, and that's good, but you can also describe it as a set. It's everything in S except TTT. I won't write them all out, but I'll do a ... here. Everything except the TTT. And then its complement would be the set just containing 3 T's. It's good to imagine these things with Venn diagrams as well. Draw a box. That box, imagine that to be your sample space. Sometimes I imagine it to be a gym floor. And events are subsets of the sample space This is A1, A2, A3, A4, A5. The intersection of any two of them is the empty set. They're mutually exclusive. The probability of their union is the sum of the individual probabilities. And it's also sometimes helpful, not that you have to do this, but it's sometimes helpful to imagine probabilities as areas. Imagine the area of the entire box, S, as equaling 1. And imagine the probabilities of each of these events, A1 through A5, as being whatever area they have. Bigger area would correspond then to bigger probability. I've drawn them all approximately the same size. And approximately, I don't know, 10% of the entire area each or so. So if that were the case, then these would each have a probability of 0.1. I made them to have no overlap. What do you do when you got overlap? Say in the case of two events. Just call them A and B. I think I'll make purposely one bigger than the other. You got two events and you want to find the probability of one or the other occurring. Remember what you have to do? Here's what I'm saying to find A or B, which is the same as A union B. What do you have to do there? It's just probability of A plus probability of B. Go ahead and talk if you want.
Probability of A union B, but then minus the intersect with A and B.
It's the probability of A plus the probability of B, yes, minus the probability of A intersect B. Because if you don't subtract it off intuitively, you've double counted this. Okay, that's not a proof. But if you don't subtract off the probability of their intersection, effectively the area of their intersection, then you're going to get it wrong. In general, A and B might have a non-empty intersection. They might not be mutually exclusive. P of A plus P of B can still be done, but don't stop there. Subtract off the probability of A intersect B. That's the general addition rule. It always works. The axiom, which is the special addition rule for mutually exclusive events, only works when those events are mutually exclusive. General addition rule. Always works. May not always be helpful, but it's always something that applies. Can be said to be true in any situation. By the way, when you solve problems with Venn diagrams, and the homework due Thursday will involve solving some somewhat practical problems to get warmed up for the subject here. Drawing Venn diagrams can certainly help. And it's good to label if you've got two blobs representing two events that could have a non-empty intersection, it's good to label the 4 different regions with their individual probabilities. So for example, maybe the probability of A occurring but not B occurring could be 0.2. The probability of B occurring but not A occurring could be 0.08 or something. Is that big enough? 0.2 and 0.08. The probability of them both occurring, their intersection, let's pretend that's 0.04. And then you'd want to figure out the probability that neither of them occurs. What do you label with the outside with? Well, these 4 sets, this one that I labeled 0.2, this one 0.04, this one 0.08, and the set outside, those 4 outcomes are all mutually exclusive. The probability of their union is the sum of the individual probabilities, but their union is the entire sample space. So what goes out here is 1 minus the sum of those by effectively this rule here, generalized. 1 minus the sum of 0.2 plus 0.04 plus 0.08. That would be 1 minus 0.32. It'd be 0.68 is what the outside gets labeled with. The outside of A union B is its complement. Does anybody know what something called De Morgan's rule says this equals in terms of the complements of A and B individually, or what would make sense looking at the picture? Here's a hint to get you started. Should I union those or intersect them? A union B is everything in here. Its complement is everything outside. Is that an intersection of these two sets or a union? Maybe you have to draw it on your paper. If you're outside of the union, you're out. Go ahead. It's the intersection. Now, if that's not immediately clear, you can draw more pictures to help you see it. You know, A and B say are right there. Their complement is everything outside. If I was thinking about the intersection of A complement and B complement, I'd be asking what's in common with what I'm about to shade green. That's A complement with what I'm about to shade purple. That's B complement. It's a little hard to see, but what those have in common is this part out here, the same thing as what was shaded over here. That's called one of De Morgan's laws. De Morgan. The complement symbol, it's like it can be distributed through the parentheses, but you got to change the union to an intersection. That works the other way around as well. A complement symbol can be distributed through an intersection, but you got to change the intersection to a union. That's true as well. That's a De Morgan law, and this is another De Morgan law, and those are sometimes useful to think about. They're not explicitly probability laws. They're just about sets, but they can be useful. Can I clarify anything? As an example with the general addition rule, thinking about our simple example with flipping 3 coins, fair coin 3 times. We could take, let's just pick particular sets. We could take A to be H, 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 T, H, T, H, T, H, H, say. So 2 or more heads. And we could take B to be, well, either all heads or all tails, say. You could say that is 0 heads or 3 heads. What's the probability of A union B in this case? Well, what is their union? What outcomes are in one or the other or both? It's not 6 elements. It's not 4 plus 2. Because there's overlap. H, H, H is in both. There's 5 elements. And the probability of A union B would be the probability of A plus the probability of B minus the probability of their intersection. Their intersection would just contain one outcome, H, 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 right? That intersection there is just the set with one element, H, H, H. Haven't talked about how to assign probabilities in this context, but it's fairly simple. If it's a fair coin, that means on each flip, you got an equal chance of getting heads and an equal chance of getting tails, 1/2. And what that means is each of these 8 outcomes is equally likely in 3 flips. Since there's 8 of them, they all have a probability of 1/8. And that also means that if you've got a subset, an event, the probability of that event is the number of elements in the event divided by 8 in this example. So for this example, these turns out to be the numbers. P of A is 4/8 or 1/2. P of B is 2/8 or 1/4. And P of A intersect B is 1/8. And in total, this gives you 5/8 for the final answer, which is obvious by also thinking about A union B as a set with 5 elements. So we're not proving this property here. We're trying to just make sense out of it. That's all we're doing. Make intuitive sense in the context of an example. Your homework problems are going to be harder than this example. Again, using Venn diagrams to help you problem solve will be something you'll need to do. Anything I can clarify? For the next set of probability properties, I think it'll be helpful to think about another example. Let's think about having a standard 52 card deck and shuffling it and picking off, let's just say, 1 card. But not everybody plays cards much, so we should probably look at a standard 52 card deck. Standard deck of cards. I have a visual here for us. Oh, it's going to zoom in here for me. There we go. Okay, so some probabilities in this context are pretty simple to think about. What's the probability, for example, of getting a queen? Well, there's 4 queens out of 52 cards for 50 seconds, 1/13. Assuming you've shuffled well, right? That it's truly random. What's the probability of getting a heart? Go ahead and shout it out. 1350 seconds, which reduces to 1/4. Probability of getting a face card, Jack, Queen, or King. $12 out of 52, which reduces to what? 3/13. So those are examples of some pretty basic probabilities that you can figure out. But then it can get a little trickier. Though that's still super hard, not terribly hard, but a little trickier. If I tell you it's a face card, what's the probability that it's a queen? One-third, yeah. 4 out of 12 or 1/3. What's that called? What did we just do? Not an ordinary probability, but a conditional probability. I told you some information. Shuffle the deck, pick 1 card at random, and I'm looking and I don't tell you what it is, but I say, hey, it's a face card. That affects your assessment of the chances that it's a queen. Instead of 4 out of 52, it becomes 4 out of 12. Conditional probability. And you know from prob and stats symbolically that we can write that in a special way. In general, you would write this for the conditional probability of A given B. That's the symbol for it. Conditional probability. The B, the thing that comes after the vertical line, think of the vertical line as given that in this context. Given that B has occurred. Yeah, the thing after the vertical line is the thing you're assuming has occurred. You want to know what are the chances that A has occurred if you know that. The formula for it is this. You take the probability of A intersect B and divide by the probability of B. This is not a theorem, really, even though it's not a theorem. It's a definition. We're saying this is what conditional probability is. It's not something to prove. Does that mean it's an axiom? Well, it's more of just a description of what conditional probability is. It's more of a definition. With definitions, you don't have to prove them, but they should make sense. You don't have to prove definitions, you prove theorems, but that doesn't mean definitions should be arbitrary. They should make sense. And so you think about whether they make sense in the context of examples. If you go back to the example here, we're after the one example that I just talked about there, the conditional probability that it's a queen, given that it's a face card. This formula says that the probability of the intersection of being a queen and a face card divided by the probability of being a face card. Now, this example is a little funny in that every queen is a face card. So the probability of Q intersect F is the same as the probability of Q. That doesn't always happen. Because every queen is a face card. Q is a subset of F. That symbol means subset. Because of that, I can simplify the formula. This doesn't always work. It works in this case. That last step, just for emphasis, only worked because I know Q is a subset of F. In general, that doesn't work. But anyway, what does it give you here? Well, the probability of being a queen is, yes, 1/13, but I can again think of it as 450 seconds, which does reduce to 1/13. And the probability of being a face card, Jack, Queen, or King, is 12 out of 52. Those 52s will cancel, giving you 4/12 or 1/3. Of course, you don't really have to use this formula to get the answer. You can just think about it with the picture. Though sometimes the formula is definitely helpful. But at least it is good to look at the formula and see that it does give you the right answer. That's good to see. Notice this is not equal to the probability, the ordinary probability of getting a queen. This is not equal to the ordinary probability of getting a queen, which was 450 seconds or 1/13. The conditional probability of getting a queen, given that the card is a face card, is not equal to the probability of being a queen. What's that called? What do we say about Q and F as events? They are not, from prob and stats. Word I'm thinking of starts with an I. They're not independent. They're dependent. They're related. Knowing that the card is a face card is information that tells you it's more likely to be a queen than if you didn't know it was a face card. The fact that you've got a not equal to here means Q and F are not independent. You could say dependent, but we usually say not independent events. They are related to each other. Most events as subsets of sample spaces are not independent. It's rare if you randomly pick two events that they will be independent. However, you might remember from prob and stats that independence is something that we use a lot. We often assume things are independent because it helps do the math to come up with models that are simpler than they would be otherwise, is the reason in a nutshell. We'll talk about why here in a few minutes. Independence is very special, but we often assume it's true when we can't actually literally list out things in the sample space and see that, oh, are these independent or not? If something seems reasonable to assume independence for, we often do, because it just makes the math simpler. It may make the math less accurate as a model of reality, but it does make the math simpler. But if it's too inaccurate, then you should go back to the drawing board. If they're not independent, what would happen if I switch the roles of Q and F here? I probably should still get a not equal to, because if they're not independent, it should be a kind of a symmetric thing. Knowing it's a face card affects the chances it's a queen. Knowing the card is a queen definitely affects the chances that it's a face card. The conditional probability of being a face card, given that it's a queen, is 1, right? Because all queens are face cards. Does it make sense with this formula? Well, only if you divide by P of Q. P of Q intersect F divided by P of Q in this case instead of P of F is 450 seconds divided by 450 seconds. 1. And that is not the same, not equal to the ordinary probability of being a face card, which is 1250 seconds, 3/13. Those are not equal. So Q and F are not independent. That is also related to those not being equal. Can I think of any independent events with cards? I claim you can fairly easily. Can you think of any events that would be independent? You could think particular kinds of cards, you could think face cards, you could think colors, you could think suits. How about being a heart? Go ahead.
If it's the probability it's an ace given that it's a heart.
Probability of being an ace given that's a heart. That's an example. Yes, that's good. Ace and heart are independent. Probability of being an ace card in general. There's 4 aces. There's 4 to 52, 1/13. The probability of being a heart. Well, let's make a heart. It's 13 hearts. That's 1/4. The conditional probability of being an ace, given that it's a heart, is what? 1/13. Yeah, how many Hearts are aces, one of them, 1 out of 13 hearts. Hey, the same. The ordinary probability of A is the same as the conditional probability of A given a heart. And again, it's a symmetric thing. The conditional probability of being a heart, given that it's an ace, should be the same as that. If you know it's an ace, of which there are 4 of them, what are the chances that that's a heart? Only one of those aces is a heart, 1/4. Those are also the same. So being an ace and being a heart are independent events. A and heart are independent events. Well, we should have done this class today on Valentine's Day, huh? A couple weeks too early. Being an ace and being a red card are independent events. Being an ace and being a black card are independent events. Being an ace and being a spade, being a queen and being a club, those are all examples of independent events. Something else really important happens with independence that is more related to its applications. So the definition of independence, the book labels this a theorem, but it's better to call it a definition. A and B, well, I'm assuming, okay, start over again. Assuming P of A is not 0 and P of B is not 0, A and B are independent events if what's true, the equality between ordinary probabilities and conditional probabilities is true. The conditional probability of A given B is the same as the ordinary probability of A, and that conditional probability is defined if the probability B is non-zero. That's why I'm assuming probability B is non-zero, because I have to divide by it in the formula for the conditional probability. And the conditional probability of B given A is the same as the ordinary probability of B. And there, in the formula for the conditional probability of this, I would be dividing by P of A, so I need to assume P of A is non-zero. That's a definition, though the book unfortunately labels it as a theorem. The next property is a theorem, though the book unfortunately labels it as a definition. And that's the most important fact from all of chapter 2. That's the most important fact from all of chapter 2. It's a fact that starts this way. Well, I'll go ahead and start it. This is a theorem here. A and B are independent events if and only if a certain equation is true related to the probability of their intersection. Does anybody remember what this equals? It involves ordinary probabilities, not conditional probabilities. Probably the most important abstract fact in chapter 2. It's the thing I said we use all the time by assuming independence. Yeah, multiply them. That's called the special multiplication rule for independent events. And again, in most applications of this, we assume independence. And by assuming it, then we can use the theorem and we go ahead and do this product. Now, again, in applying this math, you're making assumptions like that because it makes things simpler. It may be a reasonable assumption, it may not be. You have to compare the predictions of the model with reality to see if the assumption seems reasonable or not. If it's not reasonable, then your math just got harder. Your modeling just got harder. It's not that it can't be done, it's just harder. This makes a lot of formulas a lot simpler than they would be otherwise. A lot of formulas. It's a special addition rule. Is there a general addition rule? Or multiplication rule, excuse me. It's the multiplication rule for independent events. For independent events. It's special because the events are independent. Is there a general multiplication rule? Just like there's a special addition rule for mutually exclusive events and a general addition rule where we had to subtract off the probability of their intersection. Is there a general one? For the probability of A intersect B that always works even if A and B are not independent? Hint, it's related to the definition of conditional probability. Essentially, the general one can be found just by taking this definition equation and multiplying both sides by P of B. And you'll have P of A intersect B solved for. If you do that, you get P of B times the conditional probability of A given B, right? Multiply both sides of this by P of B and rearrange. That always works. So why did I say this one's more important? Well, okay, you could argue this one's more important because it's more general, but we use this one more often. But it really is a special case of this. In the case where A and B are independent, then this conditional probability of P of A given B will be the same as the ordinary probability of A, because that's the definition of independence. But wait a minute, does this make sense? I mean, is there something special about A compared to B here? Why is it the conditional probability of A given B and not the conditional probability of B given A? The answer is you can do it the other way around as well, and you should get the same thing. Even though in both of these equations, each probability could be different, the products will be the same thing. If you think about it in terms of, say, being the queen of hearts, what's the probability that your card is the queen of hearts? So by Q heart, I mean Q intersect heart, that's the queen of hearts. Well, we know the answer has got to be 1 out of 52. There's only one queen of hearts. If I compute that probability in either of these products, I should get the same answer. Probability of being a queen times the probability of the conditional probability of being a heart, given that it's a queen, is 4 out of 52, which is 1/13, times, if you know it's a queen, what are the chances that it's a heart? 1/4, right? Visualize it in your mind. There's 4 queens, only one of them is a heart. And hey, that's 1 out of 52. And if I do it the other way around, probability of being a heart is 1/4. 13 out of 52. Probability, conditional probability of being a queen, if you know it's a heart, that's 1/13. You get the same answer. The order of the numbers in the product switched, but same final answer, and it had to be. I do want, again, you guys to ask questions here. Do you want to ask some questions? It's not all of chapter 2. There's also Bayes' theorem. Anything I can clarify this? Yes, this is very quick. You have seen this before. Reading will help. You should do the reading. Remember, this book has a fair number of typos, so don't be surprised if you look at something and it's confusing. It's like, is that a typo or not? Well, it could be a typo. Maybe to end class today, in a review of probability theory, we should talk about Bayes' theorem, but maybe we should do Bayes' theorem in the context of an example. And the example I almost always think of first and put on many exams is sort of like the simplest kind of example to think of, and also is immediately applicable to, like, for example, COVID. Think about a test for COVID. You know, okay, so there's different strains, okay, whatever. There's some future strain of COVID that a certain percentage of the population has at any given moment in time. Of course, that changes over time, so this gets more complicated, but pretend it's a certain moment in time. Let's go ahead and call it C19, right? Although they're not really using the 19 so much anymore, are they? C19 for COVID-19, some other strain that hasn't come around yet. And this is a pretty rare strain. Let's pretend at the moment 2% of the population has it. So 2% of the population has this new strain of C19, and that means 98% of the population does not. Of course, as it spreads, then these numbers change. At a given moment in time, these are your probabilities. You're pretending you know them. And you've got a certain new test for this new strain of COVID-19 that either comes out positive saying you have it, or negative saying you don't. Negative would be the complement of positive. And you know from experience with COVID that sometimes tests are wrong. You could either have a false positive or a false negative. False positive is when you say it's positive, but you really don't have it. False negative is when it says it's negative, but you really do have it. Now, the probabilities that you label these branches of this tree diagram with, and by the way, this is another problem-solving tools, tree diagrams. The probabilities that you'd label these with are conditional probabilities. What's the conditional probability that you get a positive test result if you really do have COVID-19? You would hope it would be high, like maybe 99%. 0.99. And your chances of getting a false negative when you really have it would then be 1 minus that, 0.01. On the flip side, if you really don't have it, you would hope you would get a negative result. And maybe you do most of the time, but it's not as high, maybe 0.97, 97% of the time. And you get a false positive 3% of the time. If I multiply the numbers along each path of branches by the general multiplication rule, that's going to give me probabilities of A intersect B. because these are regular probabilities here and these are conditional probabilities here. So for example, the probability of a randomly chosen person both having this new strain and testing positive is going to be the product 0.02 times 0.99, which is a small probability because not many people have the strain yet. So you're giving this test to lots of people, thousands of people. You don't know whether they have this new strain or not. You don't know whether the test is going to come out positive or not. A randomly chosen person who definitely has it and the test comes out positive is pretty rare. Even more rare is that they have it and the test comes out negative. 0.02 times 0.01, which will be 0.0002. 2 out of every 10,000 people. If you got a gym with 10,000 people in it, oh boy, that's really crowded. 2 of them will have it and test negative. Is what this is predicting now in reality, because of randomness, it could be off a little bit. But most of the people are going to not have it and they will test negative. The biggest product is down here. That's 0.98 times 0.97. 0.98 times 0.97. 0.9506. And this one in here is another fairly small one. You go in that gym and you get tested and it comes out positive. You got this new strain. What are the chances that you really do? What's the conditional probability that you really have this new strain of COVID-19 given that the test comes out positive? It's nowhere in this table to be found, this probability. But using the definition of conditional probability, I can figure it out. And essentially, though I haven't written it yet, I can use Bayes' theorem, which essentially will say that for the probability on the bottom, you need to add a couple probabilities. C19N positive, that's this one here. And for the probability of being positive, in Bayes' theorem, it comes out that you need to add this one and this one. So you get 0.0198 divided by 0.0492, which is not a super huge number. It's about 0.4. Test came out positive, but you still have less than a 50-50 chance of actually having it, if this is what the data really is. Even though the test comes out positive 99% of the time when somebody has it, the chances that you have it when it comes out positive is still smaller than 50%. Why? It's essentially because it's kind of rare. Still, if this number were bigger, then we wouldn't get such a small number there. Okay. That's what we'll end class with. I'll get the homework up. Probably not right away because I got a meeting, but by 1 p.m.